So we'll start now. So we'll see the solid state. Now we have seen the three states of matter: solid, liquid, and gas. How we separate them? We can separate them on the basis of intermolecular force. Can you tell me where the intermolecular forces will be a stronger? In which case, whether in case of solid, liquid, or gas, the intermolecular forces will be stronger.
Solid.
In solid, they will be strong, right? Where it will be weak?
Gas.
In gas, it will be weak. And in liquid, I can say there will be intermediate between strong and weak, right? This is how we can classify solid, liquid, gas on the basis of intermolecular force. We can also classify them on the basis of molecular distance. Can you tell me where the molecular distance will be more? Gas, more molecular distance, or I can say long, or more also we can take. Where it will be very less molecular distance. And here in case of liquid, I can say intermediate, means between less and more, right? So this is how we can classify solid, liquid, and gas. So from these three, we have to study about the solid state today. So these are the general properties of solid. From here also we can say two things: that intermolecular distances are shorter, very less in case of solid. Second thing, we can say strong intermolecular forces of attractions are present. And we know solids are definite mass, volume, and shape. And we cannot compress the solid. That's what the fourth property we can write on. They are incompressible and rigid. Clear till this point? Now next, that important thing that we have is the types of solid. So generally solids are classified into two types. Have you studied about this thing, like crystalline solid and amorphous solids?
Yes, sir. We did it in group 15, right?
Where?
Group 15.
Group 15, crystalline solids and amorphous solids.
Phosphorus ka we did not, sir.
That phosphorus only we did. Normal in your 9th, 10th, anywhere have you studied about this thing?
No, sir.
Generally, the solids are classified into two categories. One is called as crystalline, the second one is amorphous. What is the basic difference between crystalline and amorphous? That in crystalline they will have regular shape. Means what? There is proper arrangement of atoms will be there in crystalline. While in amorphous, the arrangement of atom is not a proper. It's like we can see here. You see here. Let's say any solid is there. If there are two atoms, they can be same also, they can be different also. A B A B A B B A B A B A. Now here it is proper arrangement is there. This is the example of crystalline solid where atoms are arranged in the proper way. Clear this thing? So what is the crystalline solid? How we classify them? In crystalline solids, atoms are arranged in the proper way. There is definite arrangement of atom. When it comes to the amorphous, now look at here. A, B is there. Again B is there. Again A is there. So here it is random arrangement. A, B. Now expected that again A should come. Or again B should come, like to have the first way, to have the same like first row. But here again it is different. A, B and A. Now here A, B. So arrangement of atoms is not a proper. So when the atoms are not arranged in the proper way, those solids are called as amorphous solids. Clear the basic definition of crystalline and amorphous?
Yes, sir.
What is the crystalline ones?
Where the atoms are arranged in a definite manner.
Definite manner. And what about the amorphous one?
They're not arranged in a definite
They are
manner.
not arranged. Second thing, when we talk about the crystalline solid, they will have sharp melting point. Now NaCl is there, right? NaCl is the example of crystalline solid. So NaCl melting point is sharp. One fixed value is there for the NaCl. But when we talk about the amorphous, generally glass. So those glass, those they have the sharp melting point. Is the melting of glass started suddenly at one particular temperature, or
No, sir.
plastic?
No, sir.
No, right? So they do not have that sharp melting point. They have the range of melting point. Clear? Understand this one? Second point, second difference. You have this difference, crystalline and amorphous. Okay. Another one, crystalline solid, they have definite heat of fusion also. While the amorphous, they do not have definite heat. Means if it is a one particular fixed thing is there, then it belongs to the crystalline one. Like sharp melting point, sharp heat of fusion. If it is there, then it is the crystalline one. If it is not a sharp, then it is amorphous one. Now fourth property is like isotropic and anisotropic. Now what is this thing? Look at here now. First we'll see what is the definition of anisotropy. Anisotropy means what? The property of substance in which its physical properties such as refractive index, thermal and electrical conductivity are direction dependent. Simple thing. If properties are direction dependent, they are called as anisotropic in nature. Okay, if the properties are direction dependent, then they are anisotropic. And if properties are direction independent, then those are called as isotropic in nature. Now look at it. Here it is little bit confusing actually. See here. If I go with this row, B, A, B, A, B, A, proper arrangement is there? B, A, B, A, B, A. Proper arrangement is there or random arrangement is there?
Proper arrangement, sir.
Proper arrangement. So until and unless I have this proper arrangement, let's suppose boiling point of this entire row will be same or different? Arrangement is same. So what are the properties here? They're not only boiling point, melting point, whatever property we are studying, refractive index and all, for the entire row, that property will be same or different?
Same property.
It will be okay. This is for this row. Now if I go in this way, now look at it. What I have A. So for the entire row, not again, I can say for the entire line, property will remain same or different?
Same property.
Means if I go with this line, property will remain same or different? It will remain same. But the property here for this line and for this line, will it be same?
No, sir.
No, because here we have B A type of arrangement. When we go like this, we have A only type of arrangement. So obviously, physical properties like boiling point, melting point, they can be different, or refractive index can be a different. But until and unless I have the same direction, in one direction, property is same or different?
Same.
Properties, sir.
And if I change the direction, property will remain same or different?
It will become different.
So can I say it is direction dependent?
Yeah.
Yes, sir.
Can I say it is direction dependent? In this direction, there is one property, while in this direction, there is another property. Can I say the properties are direction independent? Sorry, direction dependent?
Yes, sir.
Okay. So here, this is which arrangement? Can you tell me? Is it crystalline or amorphous arrangement here? If you see the entire crystal proper, which one it is?
Crystal.
Crystalline.
So can I say crystalline or anisotropic in nature?
Yes, sir.
Means what? For the crystalline solid, their properties are direction dependent. For this direction, there is one property. If I change the direction like this, I am getting another property. Another property means what? That value will be different. Let's suppose if melting point here is 50, here it will be 30 for the throughout for this direction, like that. Clear this thing?
Yes, sir.
Now look at it. If I go here, first I will get A, then I am getting B. Then I am getting A. Now what is expected? I should get B. Then only I can say that for the entire direction property is same. But here first I am getting A, then I am getting B. Again I am getting A and A. So for this direction only will property remain same? For A
No,
and
sir.
it will be some, let's say boiling point for, if you check for this part, there will be some melting point or boiling point, melting point, let's suppose. For next part, that melting point will be a different, because initially it is A, B, then again A is there. So can I say here that whatever melting point is there, it is not depend on the direction actually? Because whatever the direction you go, you are not getting the unique or the same throughout the direction. Are you understanding this thing?
Yes, sir.
Look at
Yes,
it.
sir.
For A and B, there will be one melting point. Now, if I have again A and B here, I can say for the entire direction, melting point remains same. But after A and B, I am again getting A and A. So, will that melting point remain same? Will that melting point remain same here for A and A again?
No, sir.
No.
It
Can I
can.
say the properties here in this case, they are direction independent, because for if you go here first it is different, then again it is different, so it is not actually depend on the direction. Okay, now here this is which type of arrangement, crystalline or amorphous?
Amorphous.
Amorphous.
Amorphous. So can I say amorphous solids are isotropic in nature? Means what? Their properties are not depend on the direction, they are direction independent. Okay, even if you take one entire direction, in that direction itself they will have different properties. Now if I want to go in this direction, initially I will get some melting point, again it will change, so it is not depend on the direction. But when we talk about the crystalline one, for the entire direction same melting point, if I change the direction, for the entire direction same melting point. Are you understanding this?
Yes, sir.
Yes,
So
sir.
which one are isotropic and which one are anisotropic?
Crystalline and
Crystalline are
anisotropic.
anisotropic and
Amorphous
isotropic
are?
are amorphous.
Understand this one?
Yes,
Clear?
sir.
Fourth one. Now fifth one, what I have written, long range order, that is order followed for long time. Simple thing. You see here, the first one is the example of crystalline, second one is the example of amorphous. You see same order is followed for the longer time. A B A B A B, again further it will be A B A B, like a B A B A B A. So same order is followed for the long time. Okay, but when it comes to the amorphous, A B, again B A, order change. Is the same order followed here? A B A B, no, A B, then again some different order B A. For the second A B, now we expected that again it will show A B, but what is getting? A and A. So order is different. So that's the meaning here. That crystalline, they have long range order. A B A B, continuous order is there, right? For the longer time. But when it comes to the amorphous, they have short range. Short range means what you see? A B, again it changed B A. So proper order is not followed in case of amorphous. Arrangement of atoms. Huh? Understand this thing?
Yes, sir.
Okay. So till now, how many differences we have studied?
Sir, can you explain the fifth point again?
See, look at here. When we talk about the crystalline, A, B, A, B, A, B, proper arrangement is there for the long time. Means again, after this one also we will have A, B like that. Okay. So in crystalline, that arrangement is followed for the longer time. A, B, A, B, A, B. Continuous is there, right? But when it comes to the amorphous, A, B, one order is there, but the same order of A, B is not followed next. Now we are getting B, A. It is not as this A, B, right? B, A. If you go for the second line, we have A, B, expected that it should show A, B. Then I can say it is long range order. But A, B, again atoms are randomly arranged. I am getting A and A again. So can I say short order is followed here, then short range? A, B, expected that again it should show A, B. But it is showing A, A. That is the short range only is there. Means A, B followed for very short time.
Okay, sir.
Clear?
Clear.
So total how many differences we have seen till this point?
5.
5. Can you tell me again? What
Sir,
the first?
shape, melting point, and then heat of fusion, anisotropic or isotropic.
Difference I want. Means what is in crystalline, what is in amorphous. What you tell?
Okay.
So in crystalline, they have regular shape and amorphous have irregular shape.
Okay, first. Second one, any other?
Sir, crystalline have sharp melting point and amorphous are like they have like different ranges of melting point, like
Okay,
plastic and all.
okay. Third difference, any other?
Sir, for crystalline, you have definite heat of fusion, but then for amorphous, it's a range, the heat of
Okay.
fusion.
See, from this chapter, two questions are very important. The first one is that Bragg's law is there. Now, every year they are giving that Bragg's law. And the second most important thing for 4 marks is crystalline and amorphous solids. Okay, these two questions, out of these two, 101% one will come. Okay. Now, what is the third difference we have seen? What is the fourth one now? Any other? What is the fourth difference? Fourth difference.
Sir, isotropic and isotropic.
Which one is isotropic? Which one is anisotropic?
Crystalline is anisotropic. The properties are dependent on like which direction you take. Amorphous are isotropic. They're independent, like they're random throughout.
Yes. If the properties are direction dependent, then they are anisotropic. If they are direction independent, then they are isotropic. Clear? So this is the fourth difference. Fifth one, can anyone tell now? Fifth one. Fifth one.
So extended range of same order.
So can I say crystalline solid they have long range order, while the amorphous have short range order. Clear this thing? Now another difference between crystalline and amorphous solid is that crystalline solid are actually considered as the true solids, means the original solids. Okay. While the amorphous are considered as pseudo solid, like plastic. Is it the proper solid? Looks. Do you think is it proper solid plastic or rubber? We can praise, right? Rubber means it is. We can compress that rubber, so it is not exactly proper solid, right? So it is pseudo solid. Are you understanding? Which one is called as true solid? Crystalline solids are considered as true solids, while the amorphous are considered as pseudo solids. Another difference. Or they are also called as super cooled liquid. Pseudo solids or super cooled liquid. Okay.
Sir, what are called supercooled liquids?
Means if we like how we convert liquid to solid format.
We just cool it down.
So it's like we just have cooled those liquid at less temperature. That's why they converted to the solid format. That's why they're like super cooled liquid. In reality, they wanted to be in a liquid state, but because of the even at the normal temperature also, they convert back to the solid format. That's why we call them as super cooled liquid.
Sir, then what do you call ice then? Is it a solid or a supercooled liquid?
So it's generally at ice should at normal temperature, it exists in which format?
Solid.
At normal temperature, huh? Solid, huh?
Water.
Okay, liquid.
Liquid.
Yeah.
Huh? Is it super cooled liquid then?
Okay.
Okay. That is normal liquid only.
Wait, sir, can you repeat why it's called supercooled liquid?
Super cooled liquid in the sense how we convert the from liquid to solid, we decrease the temperature, right?
Yes. Yeah.
Now even if at normal room temperature, if something is exist in the solid format, then those are called as super cooled liquid. Means we cooled them just to have the solid form.
Okay.
Clear? Yeah. Now next one, crystalline solid, they have more density compared to the amorphous, while the amorphous will have less. Okay. Now crystalline are produced by slow cooling, while the amorphous are produced by rapid cooling. Means super cooled liquid, right? We just cool them to have a solid format. And the example, you can take ice, NaCl, diamond. These are the example of crystalline solid. While the quartz, plastic, rubber, tire, these are the examples of amorphous solid. Can you able to remember these differences?
Yes.
Can you remember
Yeah.
these differences?
Yes,
Yes,
sir.
sir.
Okay. Clear this thing?
Yes, sir.
Okay. You have defects for 4 marks actually, not this one. Okay. So these things we have seen. Okay. On heating, we can convert amorphous solids to the crystalline. Okay. Now there is one more question. I have written here that they have sharp melting point, right? And I also told that they are anisotropic in nature. Anisotropic in nature means what? Their properties are direction dependent or independent.
They're
And
dependent.
And I told you when I give example here that for this part there will be one melting point. For this direction there will be another melting point. So if I am saying they have different melting point, then how they can have a sharp melting point? The reason is that if melting point here, let's say if it is 50 here for this direction, and for this direction if it is 30, then that particular solid actually have that average melting point. If it is 50-30, what is the average?
40.
So it will have that fixed melting point sharp at 40. It's like average thing is there. Okay, in case of crystalline. Are you understanding what I'm trying to say? I said that the melting point is depends on the direction. And one thing I also said that they have sharp melting point. Then how it is possible? It is possible because we consider the average actually. Okay, if it is 80 here, if it is 40 here, average is what? What is the average? 60, right? So it's the melting
Sir,
point is 60. Huh?
so then why can't you consider average for the uh, isotope?
Because in case of, see, if you start that heating plastic, do you think you will get at one particular temperature that plastic will start melting?
No.
No. So it do not, that arrangement is not proper. Na? In case of here, arrangement is proper so that we can take average. But here that arrangement is not proper, so we cannot take the average. Here if you
Okay.
see AB arrangement is proper everywhere, right? So we can take the average because of that proper arrangement. But that such type of average we cannot take it here.
Okay.
Clear?
Yes, sir.
Okay. So that's the point I have written here. That one more thing, super cool liquid. Simple thing. If you have one that window glasses are there, right? And initially, if the thickness is that and top side 1 millimeter, bottom side 1 millimeter, if that same window we keep it for the longer duration, almost for 15, 20, 25 years, what happens? There is small decrease in the thickness on the top side and it's like flow down to the bottom side because of the gravity. So bottom side that thickness will increase. So in reality, it is solid, right? We are saying that it is solid, but it is like it has some liquid properties. Means who will flow? Is it possible for the solid to flow? Their atoms no. But as they are super cool liquid, so they can flow. Means like very in small. It is not properly visible. It's see almost it will take more than 20 years to have this small difference. Okay, so that's why we call it that glass is what amorphous, and it is super cool liquid. Clear?
Yes, sir.
Yeah. Now types of crystalline solids. So entire solids generally they are classified in different way. Which types of are there? Ionic are there, ionic solid, covalent solid, metallic solid, and molecular solid. What are the differences? We'll study their differences based on the property. Now in ionic solid, covalent, metallic, and molecular, what are the particles of unit cell? What is that unit cell? We'll say. Okay. So when I'm talking about the ionic solid, let's suppose take an example of NaCl, ionic compound, right? So who can be A and B atoms? What are the particles?
Na plus and Cl minus.
Both are ions, right? So
Yes.
Na plus and Cl minus, that is cations and anions. So who can be those atoms in case of ionic solid? Atoms can be cations and anions. That is the meaning. What are the particles of the unit cell? Means what are the atoms in that? So in case of ionic solid, cations and anions are the particles. In case of covalent solid, covalently bonded atoms, they are the particles or atoms. While in case of metallic solid, metallic ions with the sea of electrons, those are the particles of that cell, unit cell. And in case of molecular solid, monoatomic or polyatomic molecule. Okay, means molecular solid means what? One molecule will be there, and the it's like one solid molecule combined with the or joined together with the another solid molecule. Which forces will present between molecules?
Van der Waals
Van der
forces
Waals
and
So
forces.
the same thing. Look at here. This London forces and that Van der Waals forces, dipole. Hydrogen bond is also possible, right? So which forces of attraction? Which forces are present in ionic solid? Na plus and Cl minus. Which forces are there between Na plus? Electrostatic force of attraction, positive charge and negative charge. Which type of forces are present between covalent solid? Covalent bond. Because of the force of covalent bond, they are together. Which type of forces are present between the metallic solid? Metallic bond is there. Because of them only they are together, right? And which type of forces are present between molecular solid? Molecular solid means what? There will be one molecule and there will be another molecule and they are like joined together. So which forces are present between them? Between two molecules? Van der Waals forces, right? So they can be London force, they can be dipole-dipole interaction, or it can be a hydrogen bonding. Okay. Now, who is more harder, whether ionic one, covalent, metallic, or molecular? When we talk about the ionic, they are hard and brittle ones. Okay. Because they have large lattices. Means bigger structure will be there. Continuous after NaCl, again Na, again Cl, again Na plus Cl. Means that giant structure will be there. Diamond is there, right? So it's like it, like diamond, those giant structure are there, right? Diamond like, I'm not saying that diamond it comes here in ionic one. I'm just saying those like big structure like will be there in case of ionic NaCl. Continuous it will be Na plus Cl minus, Na plus Cl minus will be there. Then next one covalent. They are very hard. Okay, that diamond only. Next one metallic. In case of metallic, their hardness variable from soft to hard. And what about the molecular one? They are soft in nature. Okay, so these basic differences you should know. Then melting.
Sir,
Yes.
what is the example of molecular solid, like in real life?
Now we'll study that part. We have to study in detail. Molecular solids, it can be many things like CH4 molecule.
Okay. Sir, but aren't they bonded with covalent bonds?
So see, it's like if only one is there, then it is covalently bonded between carbon and hydrogen. I'm talking about the entire one CH4 joined together with another CH4.
Oh, okay, okay.
I'm not talking
Yes.
about individual atom. I'm talking about the multiple atoms. Clear? And this melting point also you can see. For ionic, it is almost from 600 to 3000. In case of covalent, it is 12000 to 4000. So who has the higher one? Here also wide range is there. Almost to the 3400 in case of metallic solids. Okay. Now their thermal and electrical conductivity. What do you think that ionic solid are they good conductor of heat and electricity? What do you think? NaCl will conduct electricity?
Molten forms.
In solid form, it will not, right? But if it is molten form, then it will conduct, right? What about the covalent one? They are insulator, except diamond and graphite. What about the metallic one? Obviously, metallic means what? That flow of that sea of electrons are there. So if electrons are there, they can flow. They can be a good conductor. And when it comes to the molecular solid, as the van der Waals forces are there, no electrons are there to conduct heat and electricity, so they are poor ones. Okay, so example you can see here NaCl. In case of covalent, diamond, silica. In case of metallic ones, NaMgCu. And in case of molecular ones, ICE, benzoic acid. Means what? Molecule joined together. We can take many things. Okay, that the same thing like ionic one conduct the electricity in the molten form. Now here this molecular solid, last column here, this one molecular, they are further classified here. They have weak force of attraction between the atoms, right? Between molecules, sorry. Now here I said three types of forces are present between them. Either London forces will be there, dipole-dipole interaction will be there, or hydrogen bonding will be there. When London forces are possible, when those are non-polar molecule. Non-polar means what? Dipole moment will be 0. CH4, dipole moment 0, H2, dipole moment 0, CO2, dipole moment 0. So how the one CH4 molecule is joined or attracted toward the another CH4 molecule, which forces will be there? London forces between them. Dipole-dipole interaction means what? It will be a polar molecule. HCl is there. H plus and Cl minus. Two poles are creating. So another HCl will be there, H plus and Cl minus. So opposite charges will attract. So they have dipole-dipole interaction. So when dipole-dipole forces are present, when it is polar molecule. And when hydrogen bonding is present, in case of FON, right? Same thing. Clear till this point, this classification? So generally crystalline solids are classified into how many categories? What are the main categories? Crystalline solid generally classified into which category?
So as ionic, covalent, metallic, or molecular?
Yes. Can you tell me the one example of all those four? Any other? What is the example of ionic one?
Sir,
Sir,
NaCl.
MgCl ions.
NaCl. Okay. Another one. I want the example of covalent solid.
Sir, diamond.
So
So
diamond,
diamond or silica.
Yes.
silica,
Good. Then next metallic solids.
sodium, magnesium,
Okay. What about the covalent solids? You can take this example also. Huh?
ice.
Covalent.
Yes, ice.
Okay. Now one more thing. What is the ionic solids are good conductor of heat and electricity?
Yes, sir. In molten form.
Uh,
It is.
Initially, we can say it is no, but only in molten form they are, not in the solid form. Okay, in molten form, they are good conductor of heat and electricity. What about the metallic solid? Are they good conductor of heat and electricity?
Yes.
Yes, sir.
Yes, sir.
What about the molecular solids?
No.
No, sir.
No. Clear this thing? Okay. Now this thing we have already seen in chemical bonding. What are the London forces and all? I have given here so that you can recall those things again. Okay. Now the main basic thing about the solid state, that unit cell and all. So what is the unit cell? It is like smallest repeating structural unit of crystalline solid. Whenever we have to study solid state chapter, now all of you are sitting in one room, right? We have to think about the room. Now what is the basic part of that room? That entire room is there which has some shape. Okay, it can be rectangular, it can be like it has a cube shape. Now if you further broke down that room, then it will have walls. Again, what is the small part in the wall?
Bricks.
Bricks are there, right? So when we talking about in case of solid state, in if we are talking about the solid, the smallest repeating part in the solid is called as unit cell. If you compare it with the house, then what is the smallest unit part? That
Break.
brick is that unit cell in case of house. Clear this thing? What is the lattice? It is 3D arrangement of unit cell. What is the smallest part is there? If you arrange them in 3D direction, okay, then it will, what are the structure will form? It is called a lattice, and obviously that lattice will have some geometry. Okay,
Sir,
yes.
how would you represent unit cells for amorphous solids?
So we are studying only about the crystalline ones because in
Oh, okay.
amorphous it is not the continuous manner, right?
Yes, sir.
Okay. So we can compare that with the room also, house also. So if you talk about the brick, that will be a what? Unit cell. Wall will be a what? Lattice. And that shape will have, it can be a cubical shape, rectangular shape. So it will have some particular geometry. Now first we have to study the characteristics of unit cell. Simple thing. Now look at here. This is what, let's say one cube is there. These lines of cube, this one, those are called as edges. Okay. You are sitting in room, right? Can you tell me total how many faces are there for that room?
6.
Six.
It's like one is top side, one is bottom, right side, left side. We can do that thing. And your front side and back side. Like you are sitting, right? Top side there is one face, bottom side is there. On your right side is there, on your left side is there. On your front side is one face, back side is there one face. So in cube, total how many faces are present?
6.
Now edges means what? These lines. These lines are there, right? This line, this line, this line, this line. So in cube, how many edges can be present?
12.
12.
How many edges? 12, right? Now this is called as edges. And the angle between edge, now look at it. This is one edge and this is one edge. So angle between edges is called as interfacial angle. Okay? Angle between edges is called as interfacial angle. So now, let's suppose if I consider this is my edge A, this is B, this is C. Then the angle between A and B, we consider it as gamma. And this thing are fixed, huh? To avoid the confusion further, we fix this thing. Means what? If A and B edge are there, the angle between A and B we consider as gamma. How to remember this thing? Simple. AB, BC and CA is there, right? In this way will be there. Angle between A and B, angle between B and C, angle between C and A. Go in the reverse way. AB is there, BC is there, CA is there. We gone forward way, right? AB, BC, CA. Now go here backward. Alpha, beta, gamma in this way. Clear this thing?
So isn't it always 90 though? Like,
Which one? Here it will be a 90 here in this case.
oh,
We form a cube, right? So it will be a 90 here.
okay, okay.
Okay. Now this unit cell, it has different types. First one is simple or primitive unit cell. Okay. Now what does mean by simple and primitive unit cell? In case of simple and primitive unit cell, constituent atoms. When I am saying constituent atom means smallest part. They are present at corner only. Now you tell me, you are sitting in a room. Total how many corners are present to that room?
8, sir.
8 corners are there, right? So now every time these atoms we consider as spherical in nature. So total how many spare? 8 corner we have. Put 8 spare on 8 corners. So each spare at one particular corner, how much contribution will be there?
1 8.
One
One,
six, one eighth, one eighth.
1
one eight
8.
it's like one spare will be there, but how much part of that spare will be present in that one entire cube at one corner? 1/8 part.
Oh, sorry.
Clear this thing? Are you understanding this thing?
Yes.
Yes.
Okay. So how many total corners will be there?
8.
8.
8 corner. And what will the contribution of atoms from the corner? From single corner?
1 by 8.
Okay. So this thing, look at here. Contribution of each particle to one unit cell. 1/8 part, because they are present at corner. So total atoms per unit cell will be how much? Total how many corners are there? 8 corners. And at each corner, how much contribution is there from the sphere or from the atom? See, total 8 corners are there. Clear this thing? Okay. And each corner is contributing how much? Means at each corner, how much sphere is there? 1/8 part of sphere, right? Look at here. We'll see here. Y add ray. Look at here. This is what the simple cubic unit cell is there. Now each atom is contributing how much here? If you form a cube here, how much contribution will be there from each sphere?
1 8.
1/8.
1/8. That's what I am asking. Okay. So from corner, what is the contribution?
1 8.
Sphere which is present at corner, how much they will contribute to the one cube? 1/8 part. Total how many corners are present?
8.
So total how many atoms are present in one unit cell? Means in one cube how many atoms will be there? See, in one cube how many atoms will be there? How we will calculate? From where atoms are coming? Atoms are coming from corner. Means those pairs are present at corner. How much contribution that each atom is doing?
1 8.
1/8. So total how many corners are there? 8. So what is the total contribution?
1.
1 8.
So this is what you have to remember, this value. In simple or primitive unit cell, how many atoms are present? Only one atom is present. In simple or cubic unit cell, simple or primitive unit cell, how many atoms are present? Number of atoms in SCC, short form we call it as SCC, simple cubic unit cell. How many atoms are present?
1 atom.
One atom. And in SCC, from where the contribution is coming?
Corner.
Corner. And total how many corners are there?
8.
8.
What is the contribution from single corner atom?
1
1
8.
by 8.
1 by 8.
This is the most important part from this chapter because this is like base we are creating for the entire remaining thing. Clear this thing? So how many number of atoms are present in SCC, simple cubic unit cell? 1. Right? Now then next is body center cubic unit cell. Now in body center cubic unit cell, constituent particle means atom, those pair, they are present at corner plus body. Now total how many corners are there?
8.
8. From each corner, that sphere is contributing how much?
1 by 8.
1 by 8.
So total contribution from corner will be how much?
For corner it is 1.
1. And another, where it is that sphere is present?
In the
Center.
center.
At body at center. It can perfectly fit at the center. Means the entire one full sphere can be fitted here. At center
Yes,
of
sir.
the cube.
Yes, sir.
You are sitting in room. Let's say you are sitting at the center part. We can place the entire one sphere there. So what is the total atoms in the sphere?
2.
2. How many are there total? 2 are there, right? So what is the number of atoms present in the BCC?
2.
2. How many are there? 2 are there, right? Clear? Okay. What about
Yes.
the space center cubic cell? Simple thing. From where the atoms are doing contribution, they are doing from corner plus space. See, corner will always be there. When it comes to the simple cubic unit cell, only corner. When it comes to the body center, name itself suggests body center. So corner plus body. Then face centered cubic unit cell. Corner plus face. Now simple thing. Corner contribution will be how much? Each corner will contribute how much?
1/8. Total.
Okay. Total how many corners are there?
8.
So
8
total
corners.
contribution from the corner will be how much?
1.
1
1 by 8.
And another where it is present that sphere?
face
Face.
Face.
Now
Six.
how many faces are there?
6.
6
6.
6 faces are there. Now each sphere, if I have to put on the face, how much contribution will be there?
half
Half. Look at here. I will show you here.
Sir, why half?
Look at here. How much contribution is there? How much contribution is there if you see here that one sphere, green one?
Half, sir.
Half is there. So each face, what is the contribution of sphere for the each face?
Half.
Half. Total how many spheres are there? Sorry, how many faces are there?
6 feet.
6
Total
faces.
contribution will be how much? From the corner, 8 into 1 by 8. Total how many faces? 6. And what is the contribution from each face?
1 by 2.
So total how many?
4.
4 are there, right? Okay. And one more thing. Yes.
Sir, are we saying like the atoms are being divided into smaller
Yes.
parts to adjust?
Yes. It's like, it is like this thing will be part in the next pair also. One cube is here, right? In front of this, there will be one more cube. So half contribution is here, half will be in another sphere, half will be another cube, right? Here we just have written one cube here, right? So one more cube will be present in front of this, means it can be joined here, next to here, like this. So when next is there, this half will be a part of this next pair, na?
Okay, sir, understood.
Okay, clear?
Yes.
One more thing that you have to remember, it's not for the IP. Like in FCC and BCC, corner atoms are not touching each other. When we talk about here, you see here, this is what the corner atoms, right? They are touching each other. Corner atom from here, touching corner atom from this side. Here also, they are touching. But when it comes to the body centered, look at here. Have they touch here? Corner atoms. Have the corner
sir.
atoms touch? No. What is the reason? Because at middle, there is one more atom, na? Because of that, they are not able to touch here. This thing is very important when we'll calculate the radius and all. Okay. So, what is the number of atoms present in the SCC?
1. 1.
FCC?
4.
4.
And in BCC?
2.
Clear this thing? Okay. Now, read this first question. Anyone you read?
A solid is formed using A and B, where A is present at corner while B is present on faces.
Hmm.
What is the molecular formula of solid?
Okay. Now, where A is present?
At the corner.
On
At corner. So, what will the contribution of A?
1.
1 by 8, right? What will the contribution of A? 1 by 8. But total, how many corners are there?
8.
So, what is the total contribution from A? Means, how many atoms of A will be there?
1.
1. What about the B now? Where B is present?
Faces.
Face. If B is present on faces, total how many faces are there?
6.
And what is the contribution of atom when they are present on face?
D.
1 by 2. Contribution of each sphere when they are present on face. Half sphere will be in one unit cell, half will be in another one. What is the contribution? 1 by 2, right?
Yes, sir.
What is the total contribution of B? How many B atoms will be there? 3. What is the formula? AB3. It's like AlCl3 type of thing. Clear this thing? Okay. Now this one you have in the exam. You read it once. Forgot about this thing, that coordination number and all. Just this one. First shoot.
A cubic solid is made of two elements P and Q. Atoms of Q are at the corners of the cube and P are at the body center. What is the formula of the compound? What are the coordination?
Now first we'll talk about the formula. Where P is present? P is present at body center. What is the contribution of atom? Those are present at body center.
1.
And so P is 1. Then comes the Q. Where Q is present?
Corner.
At the corner.
Q.
At
Q is
corner.
present at the corner. If Q is present at the corner, total how many corners are there?
8.
And what is the contribution from each corner?
1 by 8.
Total how many atoms of Q will be there?
What
1.
happened?
1. So what is the formula then?
Wait, no, no, don't worry. Just
PQ.
explaining some
What
PQ.
is the
ideas.
Sir,
formula?
Oh, wait, let me make it.
sir, I have a
PQ.
question.
Yes, yes.
Sir, how do you find coordination number?
Wait, Ray, wait. We have not studied this. Now wait.
Okay.
Now here, what is the formula?
PQ.
PQ, right? Now simple thing. P is there, Q is there. Total how many atoms are there?
2
Number
atoms.
of atoms of P are 1. Q atoms are how many?
1.
1. So total how many atoms are present in one unit cell? In that one cube?
2.
2. So it is of which type? Whether it is SCC, BCC or FCC?
BCC.
BCC. And we'll study that in BCC coordination number comes as the 8. Okay, we have those things. For BCC, that coordination number means what? How many atoms are present to the neighbors, nearest neighbors? Okay, here that coordination number here is little bit different from that in coordination compound. There it's like number of donor atoms. Here we study how many surrounding atoms will be there. Okay. Then comes the Bravais lattices. What is the Bravais lattices? Lattices which describe the crystal structure. I told right, some will be cubic, some will have rectangular, that octahedral shape, like that. Different shapes will be there. So lattices which describe the crystal structure are called as Bravais lattices. How many total are there in crystal system? Those are 7. How many Bravais lattices are there? 14. What does it mean? And I know you have not understand anything. Look at it, simple. What you have to remember here at this point, which type of crystal systems are there? And better if you remember in this way, it is easy. Ceter HMT. Ceter HMT. C stands for cubic. When it comes to the cubic, now you tell me when it is cubic. In that case, our ages A, B, and C, all three will have same that length, or it will be different.
It'll be same only.
Same.
That length will be same or different.
Same.
Same.
Same, sir.
So can I write down here A equal to B equal to C? Can I write down like this?
Yes.
All will be same. Yes or no?
Yes.
Yes.
How
Yes,
to
sir.
remember entire table, because this is very important. Simple. First we have written A equal to B equal to C. Second you write down A equal to B not equal to C. Third you write down A not equal to B not equal to C. Now again you come back to the first one. A equal to B equal to C. Again follow the same trend. A equal to B not equal to C. What is the next I have to write down then?
A
A
not equal
not
to B.
A not equal
A not equal to B not equal to C. Now one more is pending. Write down same as the last one. A not equal to B not equal to C. So when I am talking about the monoclinic and triclinic, in that the ages or their age length are they same? A, B, C.
No, sir.
Cube will have same, right? A, B, and C. All three will have same value. But when it comes to the monoclinic or triclinic, they will not have the same value. Clear? So you better remember in this way, this Ceter HMT. C stands for cubic, then tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. Okay. Now edge angle, how to remember? Alpha equal to beta equal to gamma. Simple thing. In cubic, all three will be same. Alpha, beta, gamma are different. Someone said something when I was explaining that part. That
Angle is
what?
90.
All will be the same and value will be 90. Okay. And cubic will have that number of unit cell will be 3. It's like cubic, normal cubic, we can classify in 3 categories. That it can be SCC simple, or it can be BC, it can have BCC structure, or it can have FCC structure. 3 types of structure are possible in cubic, and only we have to study cubic only. Okay, in this way we can study. Now same thing you write down for first three, tetragonal and orthorhombic. You write down same for first three. Okay. Next you write down all three are same. Alpha, beta, gamma all are same, but they are not equal to 90. Like this. Okay. Then for the next one, alpha equal to beta equal to 90 and gamma will be equal to 120. The next one is that alpha equal to gamma equal to 90 but beta not equal to 90. And the last one, all three alpha not equal to beta, not equal to gamma, not equal to 90. If you practice this for 1 to 2 days, now you will get this one. For IP, I think only little part is there, not the entire thing. Okay, so don't worry about this. Clear? I will remember in this format CETOR HMT, CETOR HMT, cubic, tetragonal, orthorhombic, rhombohedral, hexagonal, monoclinic, and triclinic. This pattern you can remember, right? A equal to B equal to C, then A equal to B not equal to C, A not equal to B not equal to C. Again the same pattern. Clear? Clear this thing?
So
Yes,
can
sir.
I ask an IP from this?
I think only short thing is there. One I forgot that one question is there. Basic only is there, not the entire one.
Okay, sir.
Yeah.
They won't ask like any long answers from
No,
this.
no, 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 no.
Okay,
From
sir.
here it is like from this part only one short thing is there.
Okay, sir.
Yeah.
Thank you, sir.
Sir,
Yes.
why cubic may we have number of unit cells as 3?
So in cubic we can have the atoms present at the corner. Always it will be there. We can have it can be one more atom can be present at center also, body centered. We can
Yes.
have the face also. So in that case we can have three structure means cubic. Further we can classify in three categories. Simple cubic, body center cubic, face centered cubic.
Okay, okay. Yes, sir, I got it.
So there like some will have 2, some will have 4. So total value here comes as 14. Means what? Basic system, how many are there? 7 are there. But those 7 again further we can make different arrangement like 14. Okay, not required that thing, don't worry. So which 3 unit cell are present in cubic crystal system? Simple or primitive unit cell, face centered and body centered. Now next one, packing fraction or efficiency. Now this part is very easy. Simple thing. How we'll study? Let's say you are present in class. Okay. There will be certain volume of that class. Yes or no? Whatever the class you are present, it will have certain volume, right? That room.
Yes, yes.
Yes, sir.
Are you guys have every time whenever you used to sit it there? Are you guys have occupied entire volume there of that room?
Oh, sir.
No,
Huh?
sir.
No.
There will be some free volume will be there space.
Yes, sir.
Are you
Yes,
guys
sir.
used to occupy the entire volume of the classroom?
No, sir.
No, sir.
There was some free space also, right?
Yes, sir.
That free space is called as voids in case of solid state, means this thing, free space. Okay. So what is meant by packing fraction or efficiency? There will be unit cell and in that there will be atom. Okay. So all the so unit cell will have some volume. Will the entire volume will be occupied by atoms?
No,
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 sir.
sir.
No, sir.
How much volume that atoms are occupying, that is called as packing fraction or efficiency. Clear the basic thing?
Yes.
Clear this thing, everyone? Do you understand the packing fraction or efficiency?
yes,
Yes.
sir.
Yes, sir.
Same thing. So same thing. Packing fraction means what? Volume occupied by particle in unit cell divided by total volume of unit cell. Now how we will find out the volume of unit cell? I told you we just have cubic unit cell in our syllabus. When I am talking about cubic unit cell, A, B and C, that edges, will they have same edge length or different?
Same age.
Same.
Same, sir.
So A into B into C. Can I write down A cube?
Yes, sir.
That part only I have written here. Volume of unit cell, A cube. Now volume occupied by particle unit cell will be equal to what? Let's suppose you all have means your weight is similar. All of you have similar weight. Then how will do like packing fraction or efficiency when it comes to the class? What we will do? Volume occupied by all students divided by volume of the class. Volume occupied by all students. How will write down? I am saying all will have same weight or all will have same volume. How will do then?
Volume
N
occupied
into
by each student into
Into
like
volume, like
number of students into volume of each student. Same way. N into volume occupied by one particle. N stands for what?
number of
Number of
number of
Number of
particles.
in case of that cube. N stands for number of atoms. N stands for number of atoms. Simple thing. When I am talking about the simple cubic unit cell or primitive unit cell, what is the value of N? How many atoms are
One, sir.
present? 1. When I am talking about the BCC, how many atoms are present?
2.
2.
So at that time I will take N value here too. Clear? Now, if I talk about the FCC, what is the value of N? What is the value of N?
4.
2.
4, sir.
FCC, who is the 2, right?
Sorry.
Sir, 4.
4. So value of N will be
4.
clear this thing. And volume occupied by one particle. Every time what we are seeing, that particle of which shape? Spherical, right? We consider particle as the spherical shape. Okay. If it is spherical, how will calculate the volume of sphere? What is the formula?
4 by 3 pi r cube.
Right? So that formula